Okay, I think now it's recording, right? Anyway, so yeah, so in this section 3.2, we discussed measures of variation. So first we discussed the range of a data set, right? And then just to remind you, so what we did the last week. So we discussed well, first the range of a data set. And then, of course, we discussed the standard deviation and the sample variance, right? So the sample variance, so the variance and the standard and the standard deviation, right? Okay. And then, so the idea is, so the variance and the standard deviation, in some sense, they show how much the values, your data values, differ from, differ from the mean. All right. And, so we have, the following. I'll just remind you the steps. So to compute the variance and the standard deviation. So, so just to remind you here. So the variance S squared, we said, it's actually equal to the sum. It's equal to the sum of the squares, right? Of the data values minus the sum of the data values squared, right, over n, and that's the size of the sample, and then the whole thing divided by n minus 1. Okay, so where n, that's the size of the sample. And x, that's the data value. Okay, and then we said, of course, the standard deviation is just it's just the square root of S squared. So S, it's just the square root of S squared. Okay. So again, so the idea is that so what you need to keep in mind, guys, if the standard deviation is small, it means that the spread of the data values around the mean is small. Okay, so if this number, if this S, so if S is small, then the spread of the data values around the mean is small. Okay, and if S is large, then this spread is going to be large. Around the spread of the data values around the mean is going to be large, right? So what do I mean by the spread of data values around the mean? I mean, the difference, the mean, that's supposed to be your expected value. So when you take a number, you take a data value, what you expect as a number is it's the mean, right? So if the standard deviation is small, what we are saying here in some sense that we are saying that if the standard deviation is small, then the difference in general, the difference between your mean and your data value is going to be small. Okay. And of course, if S is large, then the difference between the mean and the data value in general is going to be large, right? So if S is large, then the spread is large. So around the mean is large. Okay. Anyways, I think we had a couple of examples last week, Wednesday last week, and I said I think we did one exercise, right? Yeah. Anyway, so now the problem is, as I said last week, the standard deviation and the variance, they depend on the units, right? So the problem is that you cannot really compare. So if you have samples from different populations, you cannot use the standard deviation or the variance to compare the data values or compare the two samples, right? Because you are using different units. Okay, so as I said last week, Wednesday last week, there is a problem. So the problem with the standard deviation or the variance. So the standard deviation depends on the units. Okay, so you cannot compare measurements of different populations. Okay, so we cannot compare measurements or data values of different populations. So if you use like different units, you cannot compare measurements of different populations. Okay, where you use using different units. Okay, so for example, if you have a sample of like I remember the last week we had this the sample of flowers diameters. So the flowers diameters are in inches, right? So the units we use are inches. And for example, you have a second sample of for example, the weight of apples, okay? And let's say you are using ounces to measure the weight of the apples, right? So you are using two different units. So for the first sample, you're using inches, second sample, you're using ounces. So you are using different units. And so you cannot use the standard deviation to compare the two samples, right? So yeah, so then the idea now is to find or to use a different measure of spread, which is actually independent of units. And that will be the coefficient of variation. Okay, so so today we're gonna discuss so as a third measure of spread, we're gonna discuss the coefficient of variation. Coefficient of variation. Okay. So as I said, unlike the standard deviation, this is actually independent of units. So unlike standard deviation, so this is independent of units. Okay, so you can use the coefficient of variation to compare measurements of different populations, right? So we can use it. To compare measurements of different populations. Right. So let me first, I'm going to define the coefficient of variation. I'm going to give you the formula, and then I'm gonna give you an example. All right. So the definition or the formula. Okay. So yeah, so we're gonna need the mean of the sample. So let's say x bar, that's the sample mean. Okay, that's the sample mean, and then S, that's the standard, the sample standard deviation. Right. Then the sample coefficient of variation. So the coefficient of variation. So I'm gonna denote the coefficient of variation by CV. So so C dot V dot. Okay, stands for coefficient of variation. So that will be equal to. So this is equal to the coefficient of variation is gonna be the ratio between the standard deviation and the mean. Okay, so it's S, the standard deviation over X bar. Okay, so the standard deviation depends on the units, X bar depends on the units. So when you take the ratio, actually the units, they're gonna cancel out. Okay, that's how you get rid of the units. Okay, and then times 100%, so times 100%. Okay. So that's the formula. So let me give an example. So example. All right. So remember, again, guys, we have this sample of flower diameters. So example, so we have a sample of flower diameters in inches. Okay, that's the unit. So I think we had like two different hybrids, hybrid A and hybrid B. So let's say for hybrid A, so hybrid A, I think we had the following values. So for the hybrid A, I think the first flower, the diameter of the first flower is like 2 inches, then like 3, third flower, its diameter is 3 again, 8, 10, and 10, right? So anyway, so we discussed this example last week, and then we computed the mean, of course, and also, if I'm not mistaken, we also computed the standard deviation of this sample, right? So, we last week we computed. I mean, you can check your notes if you want. So we computed last week the X bar. So we said X bar, the mean, right? That will be like the sum of the, of course, the sum of all the data values, you know, like 2 plus 3 plus 3, you know, plus 8 plus 10 plus 10 over the size of the sample. We have 6 flowers, so we divide by 6, and this is actually 36 over 6. So this is actually equal to 6 inches. So that's the you know, the sample mean. So that's 6 inches. All right, and then I think we computed the standard deviation of this sample last week. S. Oops. So S, it's actually equal. So again, this was done last week. Okay, last week. So S, I think, was equal to, if I'm not mistaken, it's a 3.74. Okay, if I'm not mistaken, inches. All right. So then, yeah. So then so then if you want to compute the coefficient of variation, so then the coefficient of variation, so it's going to be equal to, so S over X bar. So the formula says the following. Here's the formula again. So it's S over X bar. So S over X bar times 100%. Again, guys, the percent means like it means like just a division by 100, right? So when you say 100%, it's actually equal to 1, right? Because it's just 100 over 100, okay? So again, just to remind you, so when you see the percent, that's just division by 100. So it's like you divide by 100. So if you have like 100%, it's just 100 over 100, right? So that'll be equal to 1. So here, I didn't really change so when I multiply by 100%, it's just the same thing. I didn't really change anything here. So it's just the ratio between S and X bar. Okay, so anyway, so in our example, the coefficient of variation is going to be, so S, it's, as I said, it's 3.74 inches, right, over X bar, which is 6 inches. Okay, this is 6 inches. All right, times the whole thing times 100. And then there's percent. All right. And as I said, guys, so as you can see, the S depends on the units, the inches. The mean also depends on the units, the inches. So inches over inches, just so it's going to cancel out. So this thing here, inches over inches, so it cancel out. So that's why the coefficient of variation is actually independent of the units, right? So now all you have to do, guys, is just to divide this 3.74 over 6. I mean, you can use your calculator, of course. You just divide 3.74 by 6. So that will be equal to 3.74 over 6. I think that's like 0.62. And then you have like 623. All right. And then don't forget, we have to multiply by this 100. So here we have like multiplication by 100. So here, this is multiplication, okay? This is multiplication. So we multiply by 100. Okay? Multiply by 100%. So when you multiply by 100, 0.62, 623 times 100, that will be 62.3. Okay, and then there's this percent, right? 62.3%. So it's 62.3%. So that's my coefficient of variation. All right. Make sense to you guys? So again, coefficient of variation is just the ratio between the standard deviation and your the mean. Yes, please. I think someone have a question, right? I'm not. Nope. Okay, no questions. All right, so you know what, guys? Let's compare the coefficient of variation of hybrid A with the coefficient of variation of hybrid B. Okay, so let's compare. Well, this is supposed to be my second example, but we can do it as an exercise. So exercise. So please, compute the coefficient of variation of so the hybrid B. So the hybrid B, we had like, again, we had 6 flowers and, all right. So I think we had like the following data values. We had like 5, 5, 5, 6, 7, and 8, right? Of course, this is, again, this is flower diameters. In inches. All right. So just to remind you guys, I mean, you don't have to compute again the X bar and S because we did it last week. So, last week, just to remind you. So last week, so we computed the X bar of this sample. It's also 6 inches. So it's 6 inches, and S, the standard deviation of this, we computed the standard deviation of this hybrid B, and it's somewhere in my notes. I don't know if you have it, guys. I think it's a 1.20, 1.26. Okay. Again, this was done last week. So this was done last week. All right. So yeah, so please, I'm gonna give you a couple of minutes to compute the coefficient of variation of this hybrid B. Okay, so please compute the coefficient of variation of the hybrid B. And then we're gonna compare, of course, we're gonna compare the two coefficient of variations of the hybrid A and the hybrid B. Layla, you got 21%. Yeah, that's perfect. Excellent. That's the answer. Absolutely. Yes. Yes, guys, absolutely. That's the answer. So, yeah, so, yeah, as you said, so this coefficient of variation, so this coefficient of variation, as you said, so it's going to be 21%. So again, it's just S over X bar times 100%. So this is actually, so S, we said it's 1.26 over X bar, which is 6. Okay, times, so this is, again, this is multiplication. This is actually multiplication, right, by 100. So we multiply by 100 right here, percent. Okay, so yeah, so that's, so 1.26 over 6, that'll be equal to 0. I think 21, right, times the 100. So that would be 21%. Okay. Now, as you can see, guys, I mean, if you compare the two coefficient of variation, I mean, for the hybrid A, we got, 62.33%. So hybrid A, the coefficient of variation was 62%, or I think 62.33%. And hybrid B, we got coefficient of variation is 21%, right? So of course, coefficient of variation of hybrid B is smaller than coefficient of variation of hybrid A, which means that, of course, that the hybrid B is more constant. Okay, it's hybrid B is less dispersed than hybrid A. Okay, so the conclusion here. So the so coefficient of variation of hybrid B is less than coefficient of variation of hybrid A. Okay, so then the values of the values or data values of hybrid B are less dispersed than, of course, data values of hybrid A. Data values of hybrid A. Okay, so again, you can use this coefficient of variation to compare, the variation of two samples, right? Is there any question, guys? So you see how this works? All right, excellent. So that's for the coefficient of variation, right? So it's just the S over X bar times 100%. And then you can use it to compare, right, the two samples of different populations, right? And of course, if this coefficient of variation is small, then the spread about the mean, the spread of your data values about the mean is small, et cetera, et cetera. So it's the same thing as for the standard deviation, right? All right, now next, guys. So next we're gonna discuss the Chebyshev's theorem. Okay, so next or now, so we're gonna discuss this, the Chebyshev's theorem. Okay, so what's this Chebyshev's theorem? Well, so the Chebyshev's theorem actually gives you the proportion of data that must lie within like certain number of standard deviation from the mean. Okay, so the idea is the following. So the idea is that this theorem, the Chebyshev's theorem. So Chebyshev's theorem, it gives you the proportion of data, the proportion of the data or the data values, proportion of the data values that must lie within a certain number of standard deviation from the mean, within a certain number of standard deviations from or above the mean, from the mean. Okay. So I'm gonna explain. Yeah. Before the examples, I'm gonna write down first the theorem. Okay. I'm gonna explain the consequence. Actually, we have a lot of consequences of from the theorem, and then I'm gonna show you an example how this thing works. Okay, how this theorem works. So let me first write down the theorem. So what does the theorem say? Okay, so here's the theorem, Chebyshev's theorem. So it says the following theorem. Okay, so for any data set, okay, it doesn't mean if it's a sample or a population. Okay, sample or population. Okay, and for any whole number, positive whole number k larger than 1, for any so for any integer, positive integer k larger than 1, so k, when I say integer, I mean positive, I mean whole number, right? So larger than 1, so k could be equal to 2, for example, or 3, or 4, or 5, etc. Right? It's just a whole number which is a positive whole number larger than 1. Okay. Then so then the proportion of the data, the proportion of the data that must lie okay, so I would say a first keyword here, guys, is must. It must lie, okay, must lie within within K. So as I said, K is just a number, a whole number, okay? Could be 2, 3, 4, or etc. Right? So within K standard deviation, on either side of the mean is at least on either side of the mean is actually is at least. So this is another keyword. At least is actually at least 1 minus 1 over K squared. Okay, so the percentage of data that must lie within K standard deviation on either side of the mean is actually at least 1 minus 1 over K squared. Okay, now, so what does it mean, this theorem? So let me explain the consequence of the theorem, consequence. So what's really important for us is just the consequence of this theorem. So consequence of the theorem. Okay. So, for example, let's say K is equal to 2, right? So, for example, let's say K is equal to 2, okay? And again, K could be any number, positive integer larger than 1, right? Now, let's say K is 2, okay? So what does the theorem say? Well, it says like the proportion of data that must lie within, so if K is 2, that will be 2 standard deviations on either side of the mean is at least 1 minus 1 over 2 squared. So then, so the theorem says the following. So the proportion of data, that must lie within, so my K is 2. So 2 standard deviations on either side of the mean is at least of the mean is at least. So when I say at least, of course, guys, I mean, of course, it can be more than, okay? At least 1 minus 1 over, so K squared, K is 2, so there'll be 2 squared, okay, if my K is 2. Now, what's 1 minus 1, 2 squared? Well, that's 1 minus 1/4, right? Now, I am going to subtract the 1 and 1/4. I mean, you can write 1 as a fraction, so you just divide 1 by 1, right? So if you divide 1 here by 1, so now 1 looks like a fraction, it's 1 over 1, right? Now you need, of course, a common denominator. So because you are subtracting fractions, you need the common denominator, and the common denominator in this case would be 4. So we need to multiply here the top and the bottom by 4, right? So that would be, anyway, so that would be 4 over 4 minus 1 over 4. So the common denominator is 4, so we keep the 4 at the bottom, and the top, you subtract the top, so that's 4 minus 1, that would be 3, okay? So that's 3 over 4. Now, you can write 3 over 4, so if you divide 3 by 4, so 3 over 4, if you use your calculator and you divide 3 by 4, that will be 0.75, right? But then the thing is, you can write 0.75 as, so this is the same thing as 75%. It's just the same thing, right? Okay, so what does the theorem say in this case? So it says like at least 75%. So at least 75% of the data values of the data values lie within 2 standard deviations on either side of the mean. Okay, on either side of the mean. So the mean. Okay, so what do we mean by 2 standard deviation on either side of the mean? So you have your number line, you know, this is your number line. Here is your mean, X bar. Okay, so on the right side, if you have if you are away 2 standard deviations from the mean, then you're gonna have X bar. So this would be X bar plus 2 times standard deviations. And on the left side, that would be X bar minus 2 standard deviations, right? So as you can see, guys, so the length of this interval from X bar minus 2s to X bar, the length of the interval would be 2s, right? This is 2s here, because the difference between X bar minus 2s and X bar, it's just 2s. And the length of this interval right here between X bar and X bar plus 2s is also 2s. So what we are saying is that your data value, at least 75% of your data values, they lie within 2 standard deviations on either side of the mean. So they're gonna be somewhere in this interval. So for example, here, okay? So yeah, so at least 75% of the data values belong to the interval, so from X bar minus 2s to X bar plus 2s, right? That's what I mean, 2 standard deviations on either side of the mean. So they belong to the interval X bar minus 2s and X bar plus 2s. Okay. I will give you a numerical example in a couple of minutes, guys. But this is the case when, so you get the 75% when k is 2, right? You can do the same thing with k equal to 3, k equal to 4, etc. So, so what you need to keep in mind from this theorem, guys, is the following. So the consequence here. So if you have, so k is 2, we got 75%, right? So we are saying, so at least, so this is when k is 2, right? So this is, so when k is 2, so we are saying at least 75% of data values, they fall in the interval you know, X bar minus 2s and X bar minus 2s and X bar plus 2s. Now, if k is 3, for example, then you can compute this 1 minus 1 over k squared. So when k is 3, so what you get is the following. So when k is 3, that will be 88.9%. So then at least 88.9% of data values, they fall in the interval. So k is 3, so there'll be 3 standard deviations on either side of the mean. So that will be X bar minus 3s, X bar plus 3 times s. Okay. And if you do the same thing for k equal to 4, so if k is 4, so what you get is the following. When k is 4, you get actually a 93% at least. So if your k is 4, then you get the following. At least 93% of your data values they fall in the interval, or they belong to the interval, in the interval. So k is 4, so that will be x bar minus 4s, x bar plus 4s. Okay.
Professor.
Yes.
Yeah, I have a question. How
Yes,
you
please.
for k for the first one, when k was equal to 2, I don't understand how you got the answer. It's not clear to me.
No, I didn't. I mean, here I didn't. I tried to use the theorem, right? So we are saying when k is 2.
Yeah.
You see
Over here, the little calculation there, I'm kind of confused.
Yeah, all you have to do actually is just to compute this 1 minus. You see this 1 minus 1 over k square.
Yes.
So what I am saying is that, as you can see here, 1 minus when k is 2, right? So
Yes.
1 minus 1 over 2 square, that will be this 1 minus 1/4 common denominator. Then you get this 3 over 4. And what I'm saying is that 3 over 4, that's 0.75. I mean, if you use your calculator, 3 over 4, that's just a 0.75. Now, the thing is, 0.75, it's the same thing as 75%. Right? Because 75% is like 75 over 100, right? The percent is just division by 100. So 75 over 100, that's exactly 0.75. So what we are saying is that, so in this case, when k is 2, we are saying that at least 75%, of the data values, they're gonna belong to this interval. X bar minus 2s plus x bar plus 2s. Now, let me give you a numerical example. I didn't give you yet a numerical example, okay? So as a numerical example, let's use the hybrid, for example, the flower diameters with the hybrid B, for example. Okay, so here's an example, show you how this, what does this thing mean? So example, and let's say, again, we have this hybrid B, okay, and the values, hybrid B, what was the hybrid B? Yes, was like 5, 5, 5, 6, 7, and 8, right? And we said S, the X bar is 6 inches, right? And the S, the standard deviation is 1.26 or 20. What was the
1.26?
26. Thank you. I appreciate it. Thanks. Inches. All right. So what does the theorem say in this case? So what we are saying, for example, at least 75% of data values. So when I say 75% of data values, so how many data values we have? You have 6 numbers, right? So when you say 75% of data values, I mean 75% times 6, okay? Because we have 6 values or 6 numbers, right? Right here, we have 6 numbers or 6 data values. Okay, so when you do 75% times 6, that's the same thing as, 0.74. Sorry, 0.75 times 6, right? So 0.75 times 6, that will be equal to 4.5. Okay, So we are saying that at least 4.5, we have 6 data values, but we're saying at least 4.5 of the data values, they fall in the interval, the interval. So let's see what's the interval here. So 75%, that's when K is 2, right? As you can see right here, 75%. So we got X bar, the interval would be X bar minus 2S, X bar plus 2S, right? So in this case, in this example, that will be the interval. So X bar minus 2S, X bar plus 2S. So that will be, so X bar, what's X bar? X bar is 6. So it's 6 minus 2 times the standard deviation, which is 1.26, right? And then the so X bar, again, it's 6. So this is supposed to be 6. 6 plus 2 times 1.26. Okay. So there'll be 6 minus, so 2 times 1.26, that's 2.52. So this is 6 plus 2.52, right? Now 6 minus 2.52, that'll be 3.48. And this is 8.52. All right. So what we are, what the theorem says is that, or the prediction made by the theorem is the following. So we are saying at least 75% of the data values, or at least 4.5 numbers, they fall in this interval. So they are between 3.48 and 8.52. So how many numbers, or how many values actually are between 3.48 and 8.52? So you see here 5. 5 is, it's between 3.48 and 8.52, right? The same for 6. 6 is between 3.48 and 8.52. Same for 7, right? And the same for 8. So actually all the numbers, or the data values, are between, or they fall in this interval. So actually in our example, so in our example, all the numbers, so the 6 numbers actually fall in this interval. They belong to the to this interval, right? The 3.48, so they are between 3.48 and 8.52. Okay, all the numbers, all the data values, they are between these two numbers, the 3.48 and the 8.52, right? But the prediction made by the theorem, actually the theorem predicted that at least 75%. So the prediction made by the theorem is at least 4.5 numbers. So the theorem actually predicted that at least 4.5 numbers. So when I say 4.5 numbers, I mean, like, it's like there are at least 4 numbers, right? There are at least 4 data values which fall in this interval. At least 4.5 numbers or data values which belong to the, or which fall in the interval. Oops. In the interval 3.48, 8.52. Okay. So of course, as I said, it's at least, right? So it can be more than just 4 numbers. So actually, the truth is, actually we have all the numbers, the 6 numbers, not just 4, but the 6 numbers, they fall in this interval, right?
Professor, I have a question.
Yes, please.
Why did you choose 75% for this example?
Now, I just said, so because the 75%, that's one of the consequences of the theorem, right? The theorem says, like, for example, when, as you can see, when k is 2, then the theorem predicts that at least 75% of the values, they're going to fall in this interval, right? So if you have, so the percentage actually depends on the you're going to see, like in the problems or the homework or the wherever. So the percentage is going to be given by it's going to be given in the problem. Okay. So for example, if you, in the problem, you see like 75%, it means that your k is 2. Okay. If you see like 88.9% in the problem, then means that your k is 3, etc. Right? So I just use the 75% because I just want to use this to see what to see this interval here. What will be this interval? The x bar minus 2s, the x bar plus 2s. Of course, I can use a different percentage. So the percentage actually it's given by the it's given in the problem. Okay. Yeah. So let me do more examples, guys. What time do we have? Okay, we have 10 minutes. Okay, cool. Yeah, let's do more examples. Let's see. All right. Okay, so example number 2. Well, let's say, so consider, let's say a sample data, data with x bar, let's say it's equal to 20. Okay, and s, the standard deviation s, is equal to let's say 2. Okay, then I want to find an interval. Find an interval let's say the smallest interval find the smallest interval in which the smallest interval in which let's say in which we can expect at least let's say 93% of the data values of data values, right? 93% of data values. So in which at least the 93% of data value they fall. Okay. So yeah, in this case, your of course x bar it's given, the standard deviation it's given, right? So this interval in which you expect at least 93% of data values to fall. So as you can see, the percentage it's given here, it's 93%. So 93% actually corresponds to k equal to, let's see, as you can see right here, right? So 93% corresponds to k equal to 4, right? So the interval would be x bar minus 4s, x bar plus 4s. Okay. So for example, if in the problem you have 88.9%, then it means your k is 3. And so the interval would be like x bar minus 3s, x bar plus 3s, right? So in our example now, we have 93%. 93% corresponds to k equal to 4. So the interval would be x bar minus 4s, x bar plus 4s. So here to answer the question, so 93% corresponds to k equal to 4. So the answer, so 93%. So in our Chebyshev's theorem, 93% corresponds to k equal to 4, right? So this is the smallest interval in which you expect at least 93% of the data values to fall. So the interval in which we expect 93% of data values to fall is actually x bar minus 4s, x bar plus minus 4s, x bar plus 4s. Data values to fall is, so because k is 4, so then the interval, right, k is 4, right? So then the interval would be x bar minus 4s, 4 times s, and x bar plus 4s. Okay. Now, what's x bar? It's given, right? X bar is 20. So that'll be 20 minus 4 times s. It's also given, it's 2, right? That's like the lower limit of your interval. The upper limit of your interval would be 20 plus 4 times 2. All right, so then, so let's just compute this interval. That's 20 minus 8, 20 plus 8. So the interval, it's actually 12, and the upper limit would be 28. Okay, so what we are saying here, guys, is that 93% of all of our data values, of our numbers, they're gonna be between 12 and 28. Okay, so so of course this is the answer, right? That's the final answer. This is your answer right here. This is the final answer, right? That's your smallest interval in which at least the 93% of data values you expect to fall. So again, so what does this interval say? So the idea here is that, so what we are saying is that at least 93% of your numbers, of the data values are between 12 and 28. Okay, they are larger than 12 and less than 28. Okay, so for example, if you have like 100, if you have like 100 data values or 100 numbers, so 93% of 100, that will be 93% times 100, so that will be 93 numbers. So what we are saying is, so if you have like 100 numbers, then what you expect is that at least 93 numbers are actually between 12 and 28. Okay, so for example, let's say we have, for example, we have 100 numbers or 100 data values. Okay, so then we expect at least, so we expect at least 93% of 100. So that will be 93 numbers. So we expect at least 93 data values or 93 numbers to be between, you know, the 12 and the 28. To be between 12 and 28. Okay. So in other words, most of the numbers, you have 93, 93 out of 100, right? So in other words, most of the numbers are actually between 12 and 28, right? That's 93%. So that's a lot, right? That's most of the numbers are between 12 and 28. That's what we are saying here. And again, guys, this is here I use this 93% because that's what we have in the in the problem, right? It says so there in the problem that they are asking for, as you can see here, the smallest interval in which at least 93%. So the percentage here is 93. That's why I'm using k is equal to 4, and that's why we have this interval. K x bar minus 4s, x bar plus 4s, because my k is 4. Now, if you have a different percentage, for example, as I said, so for example, you have 75%. So if you have like 75%, right, in the problem, then the interval, we need to use this interval here, x bar minus 2s, x bar plus 2s, because your k would be 2, right, etc. So yeah, so the percentage is just given in the problem. So it depends on the problem. All right, guys. Do we have time for an exercise or one more example? Let's see how much time. Oh, okay. All right. Yeah, so I guess, yeah, it's time to stop here, I guess. So probably next time I'm gonna do one more example or one more exercise, okay? And then we can move to the next. So we are done with this section 3.2, and so we can move to the next chapter or next section. All right, guys. Thank you for listening, and I will see you on Wednesday.
See you on Wednesday. Oh, Professor,
Yes,
when
sure.
will you read the second homework? Will it be there by Wednesday?
Oh yeah, and Wednesday. You mean yeah, the grade? Yeah, I didn't finish
Okay.
grading. Yeah, you get your grade on Wednesday. Yeah, sure.
Okay. Okay. Bye.
Yeah, see you on Wednesday.
Bye,
See you
guys.
Wednesday. Bye.
Bye. Thank you for listening. Thank you, guys. I guess I'm gonna stop recording. All right, stop recording.